So I can start now. Okay. So last time I showed that so how to define an index for general situation. For the general situation, so actually index is defined for a conditional expectation. So then the natural question is that so is there canonical condition of expectation for given subalgebra? And in a good situation, actually there is. Well, one situation is that in the case of 2-1 factors, then there is a trace-preserving conditional expectation. But for say general factor case, then there is another choice. It's so-called minimal conditional expectations. I'll talk about that. So so we are in this situation. We have either factor or say sister algebras with a conditional expectation, and we assume the existence of a basis. Right, and assume. So the index for E is defined as a central element of A, but to minimize any indices, then you need a scalar. So let's assume this condition equals the complex numbers. So A and B can be factors or just simple A and B are unitary simple sister algebras. In either case, the argument works. Right. Then in this situation, note that relative commutant of B in A is finite dimensional automatically in this situation. So I think there are many proofs of that. But one is that so you think of E, as a map from the relative commutant, say. So you consider the restriction of E to the relative commutant. Then this is a map from the relative commutant to the center of B. And by assumption, so it's the complex number. So this gives you a state. So on one hand, this gives you a state of the relative commutant. But on the other hand, you have a Pimista-Popper inequality. For any A, for any positive element in the relative commutant. So, these two condition forces that automatically. So the relative commutant is a finite dimensional. So it's a good exercise, right? For the students who just started learning operator algebra. So once if this is an infinite dimensional sister algebra and phi E is a state, then this doesn't hold. You can find you can find a norm 1 element, norm 1 positive element, and you can make this value very small. So this condition forces that the relative commutant is finite dimensional. That's one proof. Right. So so in this situation, I'm going to show you that there is a. Oh yes, but this is faithful. Yeah. Since because of this Pimista-Popper inequality. So. Right. So I'll show you that there is a unique conditional expectation. Once you assume that, so this pair has a conditional expectation with a basis, then I show you that there is a unique conditional expectation which minimizes the possible value of the index. And the key lemma is a kind of Radon-Nikodym theorem. So if we say that for any map from A to B, which is a BB bimodule map, and there exists a unique element. So it's kind of Radon-Nikodym derivative in the relative commutant. So it's unique, satisfying this condition. So M HX A, FA is given by EHA. So it's an easy consequence of the existence of the basis here. So let me give you a proof. So from the basis, from the definition of the basis, once there exists such an element H, then it should be of this form. So you just look at this here. Then you see that if there is such an H, then it should be of this form. UI star. So this at least first this shows that the uniqueness. So to show the existence, let's define H by this formula. So then the first, so we should check that H is in the relative commutant. So let's compute this. So B is in the capital B, and let's compute this. So I have been using this trick for many times, but now we expand this part by using the basis. Which way? Yes, this way. B and J with the star. Then the switch. I switch the order of the summation here. And since F is a right B module map, so I can put this into F. Then using the basis property of UI, then I get yes, B, J, star. Since F is left B module map, so you get star. So certainly, so you see that H is in the relative commutant. And in a similar computation, so now we have to check this, but it's easy. This is let's see. Yeah, this is the definition of H. UI star A. Right. So this is since A is a left B module map, UI star A. Now, so this is, again, I use the fact that F is right B module map. We get UI star A. So this is FA. So we're done. So it's a really easy lemma, but it's very useful. Right. So as a consequence of this lemma, so we immediately have the following two statements. The first one is that so any BB bimodule map is actually determined by its restriction to the relative commutant. So if F1 and F2 are BB bimodule maps from A to B.
H is unique.
What?
H. Uniqueness.
Oh, uniqueness. So if there is such an H, then by using the basis property, then it must be of this one. So it's unique. You put UI here, UI star here, then take summation. Then H must be of this one.
If there's a finite basis, then E has to be faithful. So
Yeah, that's also, yes. Yes, that's what argument also works. Yes. E is a faithful expectations. Right. So let me continue the statement. So if F1 and F2 are BB by module maps, and if they coincide on the relative commutant, then they must be the same. This is one corollary. And another one is if the restriction of E to the relative commutant is a trace, then for any H in the relative commutant and for any A in the capital A, so we have this. So HA, EHA equals to EAH. This is an easy consequence. These are easy consequences of the length. So why? Well, it's okay. So let's consider. Let's take the random negative derivative for F1 and F2. So it's okay. So exists HI in the relative commutant, such that so Fi A is EHI A. So if they coincide on the relative commutant, then it means that for any A in the relative commutant of B in A, we have this equation. So as you told, so E is a faithful conditional expectation. So this implies that H1, H. So this implies that this is Z. Well, you just put A to the H1 star and H2 star. Then you get this equation. So it means that F1 equals to F2. And the second statement, well, yes. So if H is if H is an element in the relative commutant, then you can define two BB biboundary maps. So F1. Just define F1 by, say, this way, and F2 A by E AH. Then, since the assumption is that the restriction of E to the relative commutant is a trace, so then if you define F1 and F2 this way, then you see that they coincide on the relative commutant. Of course. So first of all, since H is in the relative commutant, so this F1 and F2 are BB bimodular maps, and they coincide on the relative commutant. So by the first statement, they should coincide. So last time I said that I didn't do any Tomita-Takisaki theory, but well, here I'm implicitly doing the relative, the modular theory of the conditional expectation. So this is there's a notion of a relative modular automorphism group for conditional expectation. So this says that if the restriction of E to the relative commutant is a trace, then relative modular automorphism is trivial. That's what really it says. You don't really need to understand the modular theory at all. It's a really simple fact. So there is another lemma which is necessary to show the existence of minimal conditional expectation. Well, it's kind of also, it is also a kind of a dual operator valid weight defined in an algebraic way. So for X is the relative commutant. So we define the following map. Then, well, exactly in the same way I show that index is in the central element, you can show that this belongs to the center way. And by assumption, it's a scalar now.
So these things are also independent of the basis UI?
Yeah, right, yes. So as I showed that the index is independent of the basis, and this is independent of the basis, of course. Thank you very much. So this really depends on only E, not the basis. So this gives you a positive linear function, okay, on the relative commutant. Right, and this plays a very important role for the existence of the minimal index. Then you get index. So. Right. So let me state the restriction of E to the relative commutant is a trace. And then this map, it's not really normalized, but it's tracer functional. And it is a faithful trace. So this is also very easy, so I'll prove it.
Why that means not AGX?
What?
Why is that scalar? So close to you in the center. Why is that in the center?
Yeah, center.
E of X. E of that. That is the first class. You are not here. Okay.
Okay?
Yeah.
Okay. Okay. So about the trace. Okay. So it's easy to see. Okay, if V is a unitary in the relative commutant, then, well, so of course UI, by definition, UIs, they form a basis of E, but it's easy to show that this is also a basis. And for that, I use the property here. Yeah, using this property. Using this property, then here I assume that the restriction of E to the relative commutant is a trace. So you can use this property, and using that, then it's easy to see that this is also a basis. So this means that since this is independent of the choice of the basis, then you see you have this form. So you get this. you get a unitary invariance of this linear function. So it means that it is a trace. So this implies that H is a trace. Now I have to show that it's a faithful, but since we already know that this is a trace, well, it doesn't matter. But anyways, since the relative commutant is finite dimensional, so if there is something in the kernel, and if there is a positive element, non-trivial positive element in the kernel, then you can show that there is a projection in the kernel. So assume P is a projection. Which is in the kernel. Then by the definition of this map, so this means that so UI P is there. Right. Now I use the basis property of UI. So P should be expressed as UI star P. This is the definition of the basis. But since P is in the relative commutant and the restriction V to the relative commutant is trace, so I can move P from right to left. But since this is 0, so this must be 0. So P is 0. And HE is a faithful linear function. Okay. Right. Oh, by the way, I forgot to say that. So my presentation last time heavily relies on Watatani's monograph. So he published about I think in 90. He published a monograph of index for sister algebras. So my presentation last time relies on his monograph. And so, oh, okay. The argument I'm presenting is essentially due to Hiai. Here is the paper, modified by Watatani. Right, so now let's consider H. It's a positive element and invertible. Satisfying this condition. So consider such an element H. Then you can define another conditional expectation by this formula. So this is clearly a positive BB bimodular map, but because of this condition, it's unitary. So it is a conditional expectation. Right. And actually, you can easily see that which way? Yes, minus. This is the basis for this new conditional expectation. So the index of f, this new conditional expectation, f is given by, it's, yes, ui, h inverse ui by the definition. And this is nothing but h e.
Is that h minus half?
Minus.
Where is half?
Minus half, yes. Yeah, you put, yes, star of this thing here, then h half and h minus half cancels. Yes, this is right. So, now, our problem is the following. Problem. So minimize. So this is the index. So you fix one conditional expectation E. That's a reference point. Then what you want to do is you want to minimize this quantity. Under the condition, under this condition. So this is really a simple question. And moreover, so even if you start with a conditional expectation whose restriction is not a trace, by this trick, you can produce a conditional expectation whose restriction is a trace. So as a reference point, you can choose a conditional expectation whose restriction is a trace. So you may assume the restriction of the E to the relative commutant is a trace. So this is really a simple problem. So you have a finite dimensional C-star algebra. So it's just a direct sum of matrix algebra. So you have one trace here. Then if this is a trace, then this thing is also a trace. You have another trace. So you are given finite dimensional C-star algebra. And then you are given two traces, two faithful traces. Then you want to minimize this value under this condition. So it's a really easy application. Actually, you can solve this immediately by using Lagrange multiplier method. So I don't really want to present that computation, but that's a really easy application of Lagrange multiplier method. But here I came up with a solution. The solution is the following. So there exists a unique conditional expectation. Such that, so it minimizes. So the index of E0 is less than or equal to any possible other conditional expectation. And moreover, the restriction with E0 to the relative commutant is a trace. So this is the existence, and he got a nice characterization. Namely, given E is this, okay, such a conditional expectation is called the minimal conditional expectation.
Excuse me?
Yes?
And uniqueness is subject to the second requirement, trace requirement also, or is this further true?
Okay, so uniqueness is just here. So I should write, say, moreover. Moreover here. So it's already unique up to here. And such a expectation is always a trace on the relative commutant. And there's a really nice characterization of such an expectation. Okay, so given expectation is a minimal expectation, if and only if there exists some positive constant C such that this holds. The restriction E to let me write this way. So this trace is well, in general, this is a linear function, but anyway, is proportional to the restriction of E to the relative commutant. So this is a very easy, very useful characterization. And of course, this number, well, this number is always an index value. And well, yes.
Really say if
started right at the beginning with the God-given. Oh, no, I see. Okay.
Yeah. So this is called minimal conditional expectation. Right. So I don't really want to, present the proof, but well, given this setting, so especially so this is a trace, then it's really easy to show that. It's just well, you can give this problem to in a linear algebra class, and I think well, probably half of the students can get a solution. It's easy. I think here the main point is that he puts the problem in this form. Then it's easy to get a solution. Actually, so last year I attended a conference of the here is retirement. So he is 65 years old now, and so he's retiring now in a few days. So we have a conference for that, and he gave a speech. And when he got this result, he thought it was trivial, so he didn't want to publish it. But Kosaki forced him to publish it, and it was the right thing to do. So, since we have this really nice conditional expectation, so from now on, my definition is the following. So the index of D in A is always the index of this particular conditional expectation. So at least this notation coincides with the case of say extremal subfactor in the 2-1 setting. And the Jones projection, so I use this notation for the minimal conditional expectation. And why I use only minimal conditional expectation from now. So I use this notation.
So if you do a basic construction with respect to the minimum one, is the dual one also
minimal? Yes, dual one is also minimal. Yeah. Right. Now the next topic is the local index formula. Trivia. Then let's choose a projection in the relative commutant. Then there is a conditional expectation. So E is 0 in our situation now. So there is a natural conditional expectation from this algebra to EP. Given by this formula. So you need a normalization here. Okay, then the natural question is what is the index of this conditional expectation, or whether this is a minimal or not. That's a natural question. And actually it's easy to show that this is minimal and that to give the right formula. Okay. First, we need a basis for this conditional expectation, and that's such a natural one. Say 1. So this is a basis for this conditional expectation EP. Okay. And this is again minimal. And in particular, the index is given by this formula. So I also suppress W sign here. It coincides with the probabilistic index in this situation. So again, proof is just a straightforward computation. So let's consider. Well, let's compute this. So x is in this corner. Then we want to compute this. Yes. I forgot something. Yes. It's good. Then this is, first of all, P is in the relative commutant of B, so we can move P from here to there. And yes. And by the normalization terms of these to disappear. Yes. And well, since the restriction of E to the relative commutant is a trace and the P is in the relative commutant, I can move this P from here to there. And this is well, x is in this algebra, so this is x. Sorry? Oh, I didn't specify. Oh, P is a projection in the relative commutant. Non-zero, say. Non-zero projection in the relative commutant. Now, with the, so this shows that you get x. Okay. So this gives you a basis of this EP. Now you want to compute. Oh, you want to show that this is a minimal expectation. Okay, I already erased it, but there is a nice characterization of the minimality. So for that, I need to compute this. So x is in the relative commutant. So let's compute this. Then, yes, PUI, PX, UI star, P.
It's supposed to be BAP, you just say B.
Oh, yeah, right. So, yes. Right, so this is, yes, here you have UI, UI star. So this is nothing about, yes, HE, HEX, P. But since HE is proportional to E, so we get index of E here. And EP, EX. So by the definition of EP, this is EP square. EP square is sub PX, right? So this means that HEP is proportional to the restriction of EP to the relative commutant. And the scalar term is this. So this implies that EP is minimal. And the index, this scalar term is index. So index of EP is EP square index times EP, index of E. Right. So now we have this square term, controversial square term, actually. So this means that, if P and Q projection is a relative common, their projection is mutually orthogonal. Then, so this square term means that so index of E plus Q. Okay, let's take a square root. Then this is EP plus Q times the square root of the index and EP. Of course, this is plus EQ so we get this equation. So in other words, the square root of the minimal index is additive. Index itself is not additive, but this is additive. Right. And this fact is really important when you consider, well, actually this quantity corresponds to the categorical dimension in the fusion category language. That's why this is additive. Of course, if you start with, say, finite depth subfactor, then every trace preserving expectation is a minimal index. So you take basic construction, you get a minimal expectation.
What is it if you start with?
Finite depth.
Oh, finite depth.
So it's extreme. So then trace preserving expectation coincides with the minimal index. So everything is fine. So in other words, it's really tricky to deal with non-extremal subfactors. Yeah. It's related to the trace scaling term of the corresponding to infinity subfactor. It has non-trivial module, so to speak. Right. So this is a local index formula. And another important fact is the multiplicativity of the minimal index. So we are in the same situation. So we have A and B whose center are trivial and E is a minimal expectation. Then let's consider another algebra and expectation here. So assume so there. Well, let's assume they are, say, factors, and E and F are minimal. The natural question is that the composition is minimal. But it's a bit surprising, but it took some time to show that this is really minimal. And the original proof was really, it's involved. It's a mess. I think it's Kosaki and Long first proved it, but it's kind of mess. But now we have a really easy proof of this by using the basis. I think it's due to Watatani and Kawakami. We have a really easy proof now. So in this situation, so let's assume that UI is the basis for E, and Vj is basis for F. Then, which is the right order? Yes. So easy observation is that, of course, this is the base. Is the basis for the composition. So E, F. This is a really easy observation. Now, what we want to show that, okay. Now we want to show that, so H of Fe is proportional to the restriction of this composition to the relative commutant. Yeah. And for that, we need this lemma, which is again, it's very easy. So for any element in the relative commutant of A of C, relative commutant of C in A. This is in the relative commutant of, well, which was, yes, Vj x Vj star. This is in the relative commutant of B in A. And this is, again, very easy. It's the same kind of manipulation of basis. Right. So I skip this, but yeah. You can prove this in exactly the same way I did it several times before. So using this observation, then now easy to calculate the HFE. So let's calculate this for x in this relative commutant of C in A. And this is J, UI, J, X, J, I. Maybe I should put this summation here. UI. Then, so that lemma says that this part belongs to the relative commutant of B. So here you get, what you get is this, HE. So otherwise you cannot define. But since this part belongs to the relative commutant here, so you get HE. Right. Since we assume that E is the minimal conditional expectation, so this is proportional to E. Right. Now, Vj belongs to B, and E is, of course, a BB bimodule map. So you get this. But now this element belongs to the reactive commutant of C in B. Right. So then, yes. Is there something? Yes. We have this. Again, I assume that the F is minimal, so it should be proportional to F in the relative commutant. So and you get fx. So this shows that on the relative commutant of C in A, then this thing is proportional to the composition here.
How did you get the VJs coming out of the line that was going from there to the next one?
Here?
Yeah,
From here?
to the next one.
Oh, VJ is the basis of F, so VJ is an element of B.
Element of, oh, it's an element.
Yeah. Yes. Yes. So this composition satisfies the here is a characterization, and it simultaneously gives multiplicative of minimal index. Okay. Oh. Yeah. Now it's time to talk about sectors. But so up to here, are there any questions, comments?
So we have often run into this question of when there is a two-sided basis. Have you ever thought about that?
Two-sided basis.
Two-sided basis.
Uh-huh.
Works both ways.
For bimodule?
For some
Subfactor. No.
There is both these and their adjoint can be based.
right.
Ah. Is it possible to?
But we have no counterexample for, and I think it's impossible if it's extremal, if it's not extremal.
Uh-huh.
We have no counterexample for the existence of a two-sided basis in the extremal case.
Yeah, I've never thought about it. And actually, well, up to here, my argument. Well, I just started from the beginning. I assumed the existence of a basis,
Right.
but actually, probably tomorrow or in 2 times. So I'll choose a particularly nice basis, and they are isometries. So it's but while they give you a very cross product like expansion, and they are very useful especially when you calculate the angles between 2 subfactors. But they are isometries, so they are kind of opposite of two-sided basis. Yeah. Right.
So, is there any advantage to developing sort of a pictorial view of this stuff in terms of what is going on?
This calculation?
Yeah.
Yeah. So, what is the picture for basis?
You need the thick line. They can do this planar algebra calculus
Yeah.
in tower and so on, but you have to have a thick line on the left.
Mhm.
You're never allowed to go past it.
Mm.
And the basis element will be certain things with a thick line which will allow you to do things.
Actually, yes. So the basis, the basis I talked about right now, are intertwiners of some morphisms. So they have a pictorial explanation. Yeah, expression. Right. So now I'll talk about sectors. So yesterday Von briefly mentioned that so principal graphs are obtained from, in 2 ways. One way is to consider just a tower of relative commutant. The other way is you consider bimodule and take tensor products. Right? So I come back to that point. So let's start with the 2-1 factors. Finite index. Right. Then, so Born and also Jeff also talked about standard invariant. So let me record that. So M and time. So yesterday you learned that this nested system of finite dimensional system algebras, fundamental algebras are really important. Actually, they carry, well, in a good situation, say in amenable situation, then they carry the complete information of subfactors. The other way. Sorry. So, and Born mainly talked about how to get principal graphs from this sequence and that sequence. You get two graphs. And then you have a sequence of finite dimensional algebras. Then you get a principal graph. So, but today I will emphasize the bimodule side of this thing. So first of all, so M is thanks to the bicommutance theorem of Mare von Neumann. So M is nothing but the endomorphism space of M as a right M module. So this is nothing to do with algebra endomorphism. So you just think of M as a right M module, then you consider left module, then right module maps. Then bicommutance theorem, so M is nothing but this endomorphism space. So it means that this relatively commutant is just the endomorphism space of M as n M bimodule. So what you get here is the endomorphism space of M as n M bimodule. And similarly, well, so let's go. Well, for some reason, so I prefer to use iota for M as NM bimodules. So it's adjoint to M as NM bimodule. So here, the endomorphism space of iota bar appears. So if you know this space, that means that it's like the representation theory of finite groups. So if you know this space, it gives you the irreducible decomposition of this bimodule. Okay. Right? So what's next here? M1. So M1, well, in Bornstock, by definition, this is the endomorphism space of M as a right N module, right? Yeah. So this means that this relatively commutant is endomorphism space of M as a n bimodule. And well, this is tautological, but let me write this way. So this is a modular tensor product over M. Of course, M is the same as a modular tensor product of two copies of M over M. So let me write this way. So this means that so the next relative commutant here is identified with the endomorphism space of iota bar tensor iota. So I suppress the symbol here. What's the next one? Next one, M2. So in the same way, M2 is the endomorphism space of M1 as a M right M module. So the relative commutant is yes. So this is identified with the endomorphism space of M1 as n M bimodule. But last time I showed that M1 is basic construction is nothing but the module tensor product over n, of the two copies of m. So this shows that, again, using this tautological notation, then again, this is isomorphic. Well, should be identified with this triple tensor product. And so on and so on. So here, what you get is this. So Bon already explained yesterday. So you get this inclusion. Iota bar, iota bar tensor iota, and in a similar way, see, you get iota, iota bar, and so on and so on. So this means that once you know the category, well, I cannot say that they form a tensor category because it has a, well, it has legs, 4 legs. Well, 4 kinds of combination of legs. But well, basically, so this means that the standard invariants are given by the tensor category structure of the bimodule arising from these 2 basic bimodules. So iota and iota bar generate 4 kinds of bimodules. Say MM, MN, NM, and NM bimodules. And since these spaces are finite dimensional, that means that, you know, okay, tensor product of iota and iota bar are decomposed into irreducibles. They are decomposed into irreducibles. So now you have 4 kinds of bimodules, irreducibles. So let's start with the MM bimodules. So you here in this level you put all irreducible bimodule, MM bimodule. They could be infinite, but in a good situation, there are only finitely many irreducible. So starting with the typical one is the typical element is identity bimodule. That is M as a MM bimodule. Okay, but you get more bimodules usually. Then there's a way to produce MN bimodule. So it's yes, tensoring iota from right. Okay, so you get iota. Then you can go back from MN bimodule. So you can get MM bimodule by tensoring iota bar from right. Then you get something else, and so on and so on. You can repeat it. For example, okay. Sometimes you can get this picture.
That's so interesting.
Yeah. And you can play the same game. So here you put all irreducible bimodule. Then here you put all irreducible NN bimodule. You can do the same game. So you start from the identity object here. So it's N as NN bimodule. So to go here, what you do is from NN, I think, yes, you tensor iota bar from left. Okay? No, it should be iota. Yes. Yeah, this is iota. So from here, you go here. Then from MN bimodule, you can get NN bimodule by tensoring iota bar. So this is over N, this is over M. So you get, if I'm right, then sometimes you get such a picture. Right. So you get 2 kinds of graphs, and these 2 graphs are not necessarily the same. when the index is less than 4, then they are all the same. But well, if you go beyond index 4, then you can get two different graphs. And these graphs are called principal graphs. So you have two graphs. So I never remember which is the principal graph and which is the dual principal graph. I never remember. So let's say you have two principal graphs. And these graphs were so-called the Haar-graph subfactor. Those for the Haar-graph subfactor. Of index 5 plus square root 13 over 2. Right. So this means that, okay, so these two graphs are really important ingredient for subfactor, but usually they do not decide the subfactor completely, or in other words, they don't decide standard invariant completely. But the tensor category structure of these bimodules completely decide the structure of the standard bimodule, standard invariant. That means the subfactor is determined by, or in a good situation, the subfactor is completely determined by the tensor category structure. So that shows that these bimodules are really important. But in type 3 situation, then you can do something else. So in type 3 situation, so when M and N are type 3 factors, now assume that X is an Mn bimodule. Oh, say Mn or Mn bimodule. So very strange factor about a type 3 factor, say with a separable dual, is that there is only one representation, only one normal representation.
And now X is a Hilbert space.
Yes, it's Hilbert space. Oh yeah. So due to the fact that there is essentially only one representation of M, so you can identify this as an M, say, so the left M module structure is given by the standard left multiplication. So this is a completion of M in the GNS construction. You choose your favorite faithful normal state, then you get the same representation. Now, so this is standard left multiplication. So this means that your right action, of course, commute with the left action. So it means that your right action comes from a standard right action. Namely, this gives you that there exists row from N to M. Star homomorphism such that. So this bimodule is nothing but the standard bimodule with a twist by row. So by this symbol, I mean, so there is a natural M bimodule structure of the standard Hilbert space of M. So by this symbol, I mean that the right N action is given by this homomorphism. Okay, there is a natural right multiplication, not really right multiplication, but right module structure of this Hilbert space. Well, more precisely, the bimodule structure, bimodule is given by, if you know Tomita-Takisaki theory, then it must be given by this. So this is the modular conjugation. So this means that every information of this bimodule is encoded in single homomorphism here. So you can actually use and homomorphisms instead of bimodules in type 3 situation. And you can develop a nice theory of tensor categories or something like that with an attribution by using homomorphisms. So that's what I'm doing. I'm going to do from now. So first of all, there are a lot of structure for bimodules, the category of bimodules. One is, of course, well, in every category you have object and home space. So in the category of bimodules, home space are clear there. So in this category, so let's consider home space first. So row 1 and row 2 are homomorphism from N to N. And well, so I sometimes just write this way to describe this situation. I use this notation. Okay. So whenever I write this way, then the row 1 is a homomorphism from N to M. Okay. Then the right home space is the following. Using this identification, the right homomorphism space, home space for homomorphism of between type 3 factor is the following. So the set of operator in the target M satisfying this intertwining relation. So it turns out that this space is the right home space in this category. And actually, so this intertwiner space was introduced much before Kohn introduced the correspondences. It was already there in the algebraic quantum field theory.
Was it Roberts or?
Yeah, Roberts. Yeah. Doppler have Roberts. So this is our home space. So then once you get
Is it a simple calculation that this is the same thing as the home space between the bimodules?
yeah, actually, well, in this case, it's say antilinear. There is an antilinear isomorphism in this situation. So you can do both. So actually, there are two ways. Instead of considering this, you can also consider this. Robust. Then if you identify this bimodule and the row, then you get a linear. In this case, antilinear, but essentially you get essentially the same space. Right. So once you get a homomorphism, then you have a definition of equivalence and irreducibility. So we say that row 1 and row 2 are equivalent if they exist a unitary. So this is the so-called C-star category. So it has a unitary structure. There exists a unitary in the homo space. And we say that row is irreducible. If the home space, self-home space is, or say end space is trivial. But if you look at this definition, then this is nothing but a relative commutant. Right. So rho being irreducible means that the image is an irreducible subfactor. Right. This is the home space. So what next? Yeah. But well, this is a very nice C-star category, and especially if rho 1 is irreducible. Then this is this home space is naturally a Hilbert space. By the following inner product. So if V1 and V2 are in this home space, then this product, this belongs to the self-intertwined space of rho 1, and by definition, this is a complex numbers, so you get a scalar here. So you can introduce an inner product by this formula. So it's a Hilbert space, naturally. So the category of bimodules have more structure. So it has a direct sum. And in this category of homomorphisms, then direct sum is defined up to equivalence. This is defined only up to equivalence, namely by this formula. So where S1 and S2 are isometries in the target, satisfying these relations, the Kunz algebra O2 relation. So to make a direct sum, then you choose such an isometry. You can choose them because M is a type 3 factor. Then this formula makes new homomorphism, and but this does the equivalence class of this direct sum doesn't depend on the choice of the isometries here. So this is the direct sum in this category. And of course, the most important thing is a tensor product. And I think this part is the advantage of using a homomorphism instead of bimodule. Namely, so if you are given, say, homomorphism from N to M and homomorphism from P to N, then you need a operation corresponding to the tensor product over N. But that's obvious, right? So there is only natural operation. That's a composition. The composition gives a homomorphism from P to M. So this corresponds to the tensor product in this category. Right. And what else? Yes. So in this category, so there is a nice dimension function. So namely, okay. For rho, let's define the dimension of rho by the square root of the index of the image of N. Okay. Then it turns out that this quantity is additive and direct sum. And this essentially follows from a local index formula. This is just an interpretation of the local index formula. And this function behaves well under tensor product composition. So it's a multiplicative. And this also follows from the multiplicativity of the minimum indices.
So you need a basis. To have a minimal But when next formula you need is basis.
Yes.
So you haven't shown us that there's basis.
So now we are in. Okay. Of course, now I'm a bit cheating because, well, so let's assume everything is finite. Then it already assumes that the image has a finite index. It means by definition there is a basis.
Type 3 case.
Type 3 case. Now everything is a factor. Yeah. Right. So that's why I want to stick to the local, the minimal conditional expectation, because then you can define nice dimension functions. So I use this notation sometimes. Okay, the equivalence class of such homomorphism is called a sector. And so I use this notation for the set of homomorphisms from, say, unitary homomorphisms from n to m divided by equivalence relation.
So if you were in the type 2 situation, could you not do exactly the same thing by having sectors from homomorphisms from n to the matrices of that?
Oh, yeah, you can. Then you can do similar thing. Yeah, but every time you need to go to the matrices. Yeah.
For DSP composition, you have to amplify in length approach.
Yeah. Yeah, composition is a bit complicated. Yes. Right.
And the set you define only when it's finite index? Or in general?
In general, you can define it, but of course, it's
The good results are better.
yeah. The subset of finite index homomorphisms are mostly important. So I think it's time. That's the field.